Okay, 2.3, finally going to start learning some shortcuts. We're going to learn power rule, product rule, and quotient rule. So first today on this video, we're going to do the power rule for 2.3. What I'm going to do is I'm going to do some examples of it, and then we'll talk about why it works, okay? Now, the rule is real simple. Whatever the power is, you bring it down, and you reduce it by 1. And that's it. You must follow the rule, okay? I cannot say that more rigorously. Follow the rule. You bring the power. In other words, don't make up your own rules just because it looks weird. Always do the same thing every time on this, okay? If the variable is there and there's a number there, the rule is to bring the power down and reduce it by 1. And you might think, oh, that's so super simple. And it is, okay? It's not hard, but you'll see. So when you take the derivative, now when we call this either the derivative of y, or sometimes we call it dy dx, the rate of change of y over x, because we want to remember it's a slope, right? Either way is fine. I don't care whether you use the little prime symbol. Newton and Leibniz were the ones that did this. I don't know, one did the other, and I don't know which one's which, but this is the two main ways of doing it. But either way, the answer to this question would be 4x to the third plus 21x squared minus 12x minus 7 plus 0. Now, the rule is bring the power down and reduce the power by 1. Remember, the derivative is a slope. Okay, don't forget that, because we're going to remember that at the end here. So the derivative is a slope at a point. So 4x squared, and then again the rule is bring the 3 down. 3 times 7 is 21. Reduce the power by 1. Bring the 2 down, 12. Reduce the power by 1. Now remember, 7x, if you have 7x way back even in algebra, we knew that slope is 7. And then if we have a constant, we know like y equals 1, the slope is 0, isn't it? Now we don't normally write the 0, okay? We don't normally write the 0. So again, this is the rule. It looks a little funky at the end, but the rule actually holds there as well. But just use common sense here. What's the slope of negative 7x? The slope of negative 7x is 7, and the slope of 1 is 0. Now, what I mean by that, the rule technically works. You don't do this, okay? Just know the slope is 7, and then that's 0, so we don't normally write it, right? You could say that negative 7x, the rule, you bring the power down, bring the 1 down, and subtract 1. And of course, x to the 0 is 1. 1 times 7 is 7. So it does work. Here, you could argue that this is x to the 0. Bring the 0 down, x to the negative 1. Well, 0 times anything is going to be 0, isn't it? So, you don't do it that way, but yeah, technically the rule still holds, right? You still use this blue rule. But normally when it comes to lines, we know that 7x has a slope of 7 and the 1 constant has a slope of 0. Now, this is all nice and dandy, right? You just bring the 4 down and 3. If this was our life, then it would be super easy, right? Okay, well, what if it's a little more complicated? What if it's 5x to the 1/2 plus 7x to the negative 1 minus 3x to the negative 1/2 plus x to the negative 2? Now, notice what I did there. I want to make it look like x raised to a power, right? So I change the square root to a 1/2. I bring that upstairs, making it negative 1. Bring that upstairs, make it a negative 1/2. Bring that up to negative 2. So what I did there, of course, is I changed it so it's all x to the n. And then what would you do if you want to take the derivative? Bring the power down and subtract the power. 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 Don't change the rule. You bring the 1/2 down. half times 5 is 5 halves. Subtract the power. Bring the negative down. Negative 1 times 7 is negative 7. Subtract the power. Bring the negative down. A negative times a negative is a positive. 3 times a half is 3 halves. Subtract the power. Bring the negative 2 down and subtract the power. So that's the rule, okay? And it's not that bad. Now, we're going to learn a product rule and a quotient rule, but even on these two, I wouldn't use a product or a quotient rule. I'd actually work it out. How do you do these ones here? Okay, how do you do these ones here? We've got to FOIL it out first. So what's that? 15x to the third minus 6x squared plus 5x minus 2. So what did I do here? I multiplied it out, first times first, outside, inside, last times last. So what did I do? I changed it into the question we already did, kind of, right? That's the idea, right? Yes. When you have a product, we're going to learn something called the product rule tomorrow, but for right now, let's just do it this way. And even so, this is still the best way to do this question, to be honest. Again, the rule, bring the 3 down. 3 times 5 is 15. No. 3 times 15 is 45. Subtract 1. 2 times 6 is 12, but it's negative. And again, the derivative of 5x, remember derivative means slope. So this slope is 5, and this slope is 0. And as you could probably imagine, same thing on this one here. In the same way I multiply this out, divide it in. Divide that x into everything. X plus 1 plus x to the negative 1/2 plus x to the negative 1. So x squared divided by x is x. X divided by x is 1. Square root of x divided by x, there's a half power of x in the bottom, but it comes up as a negative. 1 over x can be written as x to the negative 1. So again, you want to rewrite, you want to do the division and you want to rewrite it so it looks right. And then we take the derivative. So I get 1 plus 0. You don't have to write the 0, but I'll get rid of it in a second. Minus 3 has minus x to the negative 2. The derivative of x is 1. Remember, there's a slope of 1 there. The constant's 0. We normally don't write it. Bring the negative 1/2 down and subtract 1. Bring the negative 1 down and subtract 1. And again, we don't normally write the 0. Now, why does that work? Why does this work? Now, I want to be very clear. This is not a proof. This is not a proof of why it works, but it hopefully will get you to see why it works. I'll talk about why it's not really a proof in a second. You can kind of call it a proof for integers, but let's see what happens here. So the derivative, let's just pick x to the third for right now. That's kind of like x to the n. So I get limit as h goes to 0 of x plus h to the third minus f of x. Oh, sorry, which is x to the third. Sorry, brain stall. Over h. Okay, now we have to FOIL that out. Now I'm going to use Pascal's triangle to do that. Remember how you do Pascal's triangle? You put ones on the diagonal, and then you add the two. So it has to be 1, 3, 3, 1. And then x to the third, x squared, x, and then the h is h to the third, h squared, h. Just using Pascal's triangle, or what we call binomial expansion, right? Minus x. You could FOIL it out the long way, but I'm heading somewhere with using Pascal's triangle here. Over h. So then the x to the thirds cancel. Now notice what happens here. We want to kind of see a pattern forming here. Notice that that has an h, that has more than one h, and that one has more than one h. So the only thing that's going to survive this is the 3x squared, right? Because even if I factor the h out, 3x squared plus 3xh plus h squared over h, and you cancel out the h's, the other h's are still going to go to 0. So notice that the only thing that's going to survive is the one term that has the one h in it. Let's try that again. Okay. What if I do x to the fifth? So if I want to FOIL that out, I want to use Pascal's triangle. 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. So this would actually FOIL out to x1, 5, let me get rid of the x right now, 1, 5, 10, 10, 5, 1, and then we start with x to the fifth, x to the fourth, x to the third, x squared, x, and then here h to the fifth, h to the fourth, h to the third, h squared, h. And then we're going to subtract the x to the fifth all over h. So this here is that FOILed out for that, and then that. Now here's again, watch what happens here. Watch what happens here. Notice that, and this is what you want to think. The first one always goes away because it always goes away with the f of x. Now here's the important thing. This is the only term with an h in it. These have more than one h's. So even if I cancel the h's out, they're all going to go to 0. So here's the thing you want to see. The only term that's going to survive as I go down this line here is the first term. So let's look at x to the n now. So if you look at x to the n, here, if you look at x to the n here, when you do the f of x plus h, here's the thing. It's always going to be x to the n plus nx to the n minus 1, h plus, and the dot, dot, dot. Remember, the dot, dot, dots don't matter because they're all going to have more than one h in it. Even if I cancel that h out, they're all going to go away. And then this one's going to go away. Oh. So notice that that's what you end up with when you're done. You know, I actually canceled out, that's going to cancel out here, so this really isn't that, but hopefully you can see what I'm talking about. Is notice that that's the only term that's going to be left, because all the that one goes away because it's going to be subtracted, and then all the other h's powers are going to go up, h squared, h third, h fourth. So I don't even care; they're going to go to 0 eventually. So the only term that's going to survive is that first term of the Pascal's triangle, which is going to be that term, and that's an explanation. Now that's not a proof; that's just an explanation. Because notice one thing, you could argue that maybe I kind of proved it for integers, but clearly that binomial expansion only works for integers, right? I didn't prove it for like fractional exponents. You're gonna kind of have to take my word for it that it works for that. The proof for that's a little bit complicated. Okay. To actually do the full proof of this is a little bit beyond our abilities right now, but. I think I did a pretty good job of showing you that it pretty much works. Okay, that's the power rule.